So now we're going to do composition with inverse functions. Inverse trig functions, to be specific. So if x is in the domain of sine inverse, then sine of sine inverse of x equals x. That's if x is in the domain of sine inverse. Okay. If not, then sine of sine inverse of x has no solution because you can't do sine inverse of x. So that's clear enough. The same is true for the other trig functions. This is composing a function with its inverse in this particular direction. So composing in the other direction, the other order, causes a different kind of complication. Okay, for the square root and square example, square root of x squared equals x if x is greater than or equal to 0, or opposite of x is negative 0. In other words, square root of x squared is the absolute value of x. But there's two rules. This is because squaring function is not one-to-one. The situation for inverse trig functions is similar, but it's actually worse because the trig function are periodic. They're not just not one-to-one, they're actually periodic. So you don't just get two rules, you get several, infinitely many. So to find S inverse of sine inverse of sine x, we cannot just cancel sine inverse and sine to get x. Doesn't work. This is with the arc sine or the inverse function on the outside. Okay. We need to find x's so that sine of x prime, so that sine of x prime equals sine of x, and x is in range of sine inverse. And of course, I'll do an example. The easiest way to do this is by using the CS plane, which means you're basically using triangles most of the time. The first condition is satisfied by two different terminal sides. Angle x prime will come from one of these two terminal sides. Okay, so we have to kind of see how this works in order to make any sense out of this.